All right, let's start. So last time we reviewed a little bit about the determinant, and there are many interesting properties, but today the main properties that we utilize is this guy. The determinant of the product of the matrix is the product of the determinant of these matrices. Okay, so yeah, so we have these two properties, and also so before moving on, let's review these two additional items that we add to our invariability theorem, or invariable matrix theorem. So if the matrix is invariable, and then it means the eigenvalue of an A is not 0. So 0 is not an eigenvalue. In case determinant of an A is invariable. So in this case, so we will make this part non-invariable, right? By carefully choosing a particular lambda. But if we just simply choose lambda as 0, and then it will be just same as determinant of an A, and so it means this guy. So if lambda can be 0 or eigenvalue is 0, and then it means determinant of an A is 0, and thus the matrix is not invariable. Okay. Okay, then let's move to this new topic called similarity. So given a matrix A, so we consider the following transformation of this matrix A into another matrix, for example B. Okay, but B is defined as this transformation of the original matrix A. In other words, we multiply some matrix on the left, and then its inverse on the right, and P is square matrix, of course, and also A is a square matrix as well. Okay, so still we only consider the square matrix, and we just multiply some the same size of a square matrix that is invariable, and if we just multiply that on the left, and then it's the inverse on the right, and that is called the resulting matrix is B, for example. In this case, this transformation from A to B is called similarity transformation. And also, if matrix B can be obtained by this transformation of an A by using some arbitrary matrix P, okay, and then we say matrices A and B are similar, or A is similar to B. And what's the meaning of this being similar between the two matrices? I mean, in what aspects are these two matrices similar? So these similarity is thought of in terms of the eigenvalues. Okay, so here A and B are actually sharing the exact same set of eigenvalues. Okay, so you guys remember like row equivalent. So if we change the matrix A through the row reduction or Gaussian elimination into some of it's an echelon form matrix, and then what stays the same, or what kind of common characteristics are shared between the input and the resulting echelon form matrix? The solution set, right, for the linear system of an AX is equal to B, right? Even if we transform a given matrix into echelon form, when viewing it as two different augmented matrix and considering their own, two different linear systems and their solution set, will exactly be the same, right? And also, yeah, kind of similar to that. So here, what are staying exactly the same? The eigenvalues of an A is exactly the same as eigenvalues of B. And more exactly, the characteristic equation or characteristic polynomial will be exactly the same between the two matrices A and B. Okay, so so let me just briefly show or prove they share the exact same same eigenvalues and thus the same characteristic equation. So this is the characteristic polynomial. I mean, if we set it as 0, it is called the characteristic equation. And then if we just consider this nth order polynomial of lambda, that is called characteristic polynomial. Okay? And then the characteristic polynomial of an A is the same as characteristic polynomial of B. Okay? So I'm going to show you or prove this relationship. So this guy, determinant of b minus lambda I is determinant of p inverse minus lambda I, right? And then for this matrix I, let's change it into p times p inverse. Okay, and then also we just put I here, and then it can be written as p times a minus lambda I times p inverse, right? So in other words, like A and B minus C and D is the same as ABD minus ACD. Okay, so how can we prove it? I mean, it looks quite obvious, but proving it requires maybe just a few steps, like AB minus AC by applying the distributable law, and then times D, ABD minus ACD, right? So if we start with this guy, and then we can factor it out into the left hand side, right? So this guy, so this part is P times lambda I times P inverse, and thus we obtain this kind of factorization, right? Okay, and then now we will apply the one of the properties of this determinant, which is this guy, right? Then it is determinant of P and determinant of A minus lambda I and determinant P inverse. And we know that this guy and this guy, when multiplying them together, they will become 1, right? So yeah, so if we have a 2653 and computing is a determinant as like -24, right? And its inverse matrix will have the determinant of 1 over -24, right? And so multiplying them together will always produce 1, and thus it will be determinant of A minus lambda I, which is the same as this guy. Okay, and so A and B shares the exact same form of characteristic polynomial. And by the way, this equation, I mean, in order to satisfy this equation, does it require any particular lambda value, or will it be always satisfied for whatever lambda value is. So again, is it like always true for any lambda, or is it only true for a particular lambda? So it is always true, because in this proof, in this all the steps that we used to prove these two are the same, we didn't require any of the specific conditions or requirement for lambda. So it should be the same as for any lambda. And it means in Korean, 그러니까 항등식이란 뜻이 항등식, 두 개 람다에 대한 다항식이 항등식이라는 뜻이에요. 그러니까 두 개가 식이 정확하게 똑같다는 거예요. 그러니까 람다에 대한 기본적으로는 n차 방정, n차 다항식인데, 다항식이 두 개가 똑같으려면 그 계수값이 n차, n-1차, n-2차, 그리고 0차까지 혹은 상수까지 완벽하게 똑같다는 뜻이에요. 즉 그러니까 그 캐릭터리스틱 폴리노미얼, 그 특성 다항식이라고 그러나요? 그걸 써보면 완벽하게 똑같다. 그러면 그것의 캐릭터리스틱 이퀘이션에 대한 근도 완벽하게 똑같겠죠. 그렇죠. 그래서 이제 솔루션 셋 혹은 이 방정식의 역시 이 다항 방정식의 솔루션 셋인 그 람다의 해들이 완벽하게 일치한다. So they share the exact same set of lambda as the solution for this characteristic equation. Right. And so and also for this, we can easily change it in terms of the row of input and output. So we just multiply P inverse P over here, and then A will be obtained like P inverse B and P, right? So B is transformed into A through its own similarity transformation. But anyways, the similarity transformation preserves the original eigenvalues. Okay, so that is the point. So this is the proof about it. And let's consider these two matrices. And are these similar to each other, or will it be possible to change or transform one matrix through the similarity transformation into the other? In order to verify they are similar or not, we can just write their characteristic polynomial. So in this case, 2 minus lambda squared minus 1, right? And this guy, 1 minus lambda and 2 minus lambda, right? The polynomial is different, right? So they are not similar. Although, if we just compute the eigenvalues, what's the eigenvalue of it? It is 2, because it's an upper triangular matrix. Upper triangular matrix will reveal all the eigenvalues on its diagonal elements. Okay, so it will have 2 as an eigenvalue. It should be 0, right? Okay, so this is characteristic polynomial, and this is different one, right? And then these are also diagonal matrix, which is a special case of an upper triangular matrix, and thus 2 and 1 are eigenvalues, and they share one of the same eigenvalues as 2, but the characteristic polynomial itself is different, right? So in the next chapter we will actually consider carefully this number. This is called the multiplicity, and the multiplicity found from this factorization form is called algebraic multiplicity. So it's like, so we have the solution of 2, but we have two of these solutions, two of the same solution of 2, right? So that's the meaning of this. 그러니까 중근, 반복된다 해갖고 그걸 중근이라고 하죠. And this multiple solution, 그러니까 중근이죠. This multiple solution is purely found from this factorization of this equation or polynomial, right? Characteristic polynomial, right? So we found this multiplicity purely from this polynomial or just written mathematical expression, and that's why we call it as a algebraic multiplicity. But are there any other multiplicity then different which is different from algebraic multiplicity? Yes, it is. There is something called the geometric multiplicity, which is much more interesting, and that is related to that. That is actually, let me just directly explain what the geometric multiplicity is. So in this case, we have 2 as one, distinct eigenvalues. So here the characteristic polynomial is second order, but because we have these multiple solutions, right, in terms of different values, we only have one different or one distinct value of an eigenvalue, right? But we have 2 as multiplicity of this solution, right? But anyways, suppose we found this says one eigenvalue, and then we just form this a minus lambda I. So if we just find a minus lambda I, and then it will become 0, 0 and 1, 0. So that is a minus lambda I from this matrix, right? And then let's consider an x1 and x2 and 0 as a homogeneous linear system, and then if we find the general kind of parametric vector form for this homogeneous linear system, and that is eigenspace corresponding to or associated with this eigenvalue, right? And then we can also we can consider the dimension of this eigenspace, right? And so this dimension of the eigenspace is called geometric multiplicity. So here, how many dependent or independent variables? So this is the only pivot, and this is an dependent and independent, right? In terms of the columns, whether each column has a pivot or not. And so here, the dimension of the null space is the same as the number of this non-pivot columns, or the number of free variables, right? So we have only one free variable over here, and so the dimensionality of this eigenspace will be only 1, right? Only 1, and that is called geometric multiplicity associated with this particular eigenvalue. Okay, so in this case, the eigenvalue 2 has algebraic multiplicity, and also we can think of this geometric multiplicity. Okay, so in this case, what's the algebraic multiplicity for this lambda? It is 2, because we see 2 over here. Okay, but geometric multiplicity is simply the dimension of the corresponding null space, and it is 1, right? And in general, if we think of like n by n matrix and consider determinant of an a minus lambda I, which is the characteristic polynomial, and then set it as 0, and then let's imagine it's like solution as maybe a and 3 and a minus lambda minus b 2 to the power squared, and c maybe 5 and something like that. Okay, so in this case, lambda algebraic multiplicity and geometric multiplicity. Okay, and lambda, suppose a, b, and c are distinct roots or solutions. A, b, and c. Well, let's say it's 1, 2, 4, for example. Okay, it's 1, 2, 4, and 1 has a geometric multiplicity of 3, 2, 5. And it means it is 10 by 10 matrix, because in total we have a 10th order polynomial, right? Okay, and now what geometric multiplicity, which is the dimensionality of its null space or eigenspace corresponding to each of our eigenvalues. So it will be at least 1. Can it be 0? If the null space dimension is 0, and then it means we have no free variable, but yeah, this lambda, okay, lambda is the solution for, the solution that makes this, the determinant of this guy to be 0, and it guarantees at least one free variable or at least one linearly dependent column of our matrix, right, of an A minus lambda I. So it will be at least one geometric multiplicity or the dimension of the eigenspace. And will there be any upper bound? The upper bound is actually 3, 2, 5. Okay, for some matrix, this root has algebraic multiplicity of 3, and if we compute their parametric vector form of the homogeneous linear system of A minus lambda I times x is equal to 0, and then if we compute, or if we just count the number of free variables, and the free variables will be at least 1, but the maximum number of free variables that we can have is 3. And for this value, 2 and 5. I mean, we will not prove this, but in general, this geometric multiplicity, which is the dimension of the eigenspace, is the same as or equal to or smaller than the algebraic multiplicity. Okay, and also let me ask one question over here. So it is a 10 by 10 matrix, and what is the dimensionality of our null space, or the solution of homogeneous linear system? A minus lambda I will still be 10 by 10, and so this is our x, right? And this is 0, right? And so x is still living in 10-dimensional space, right? So it's in the 10-dimensional space. Okay, and if you remember one interesting properties, so this eigenspace and this eigenspace and this eigenspace, do they overlap with each other, or so if you guys remember this theorem, if the eigenvalues are different from each other, their corresponding eigenspace will not have any overlaps, and it means you choose any vector from the eigenspace of lambda 1 and another vector, any arbitrary chosen vector from the eigenspace of a different eigenvalue. In that case, those two vectors are always linearly independent. Okay? So in that sense, they have always some non-zero angle between the two vectors. And thus, if we consider the two subspaces, two different eigenspaces, and then they will coincide only at the origin. Okay? And there is no other overlapping or common vectors that they have. Because in that case, if we choose such an overlapping vector, and then those vectors will be linearly dependent with each other. But here in this theorem, if the eigenvalues are different, they will be automatically linearly independent, and thus they have no overlaps between different eigenspaces. Okay, so in this case, so how many, what will be the sum of all these numbers? It will be 10, which is the total, total dimensionality, right? If we happen to have some complex root or solution, and then it will be strictly less than 10. But suppose we were able to find all the real solutions or roots of 10th order polynomial of this characteristic equations. Okay, so it will be always 10, right? And so let's suppose these guys, I mean, we have no such restrictions like this. And then suppose, we have maybe geometric multiplicity as maybe 4, which is greater than 3, and maybe 3, and maybe 4. Okay, so in this case, these 4 are linearly independent vectors within that eigenspace. Does it make sense? I mean, what's the dimensionality of eigenspace? Linearly independent vectors that we can find from that eigenspace. Or we have 4 linearly independent basis vectors from that single eigenspace, right? Right? So this 4 is the same as the number of free variables of a minus lambda I, right? And we have, suppose we have 3 and 4. Okay, so within each eigenspace, we have 4 linearly independent basis vector, 3 and 4 linearly independent eigenvector. In overall, is it possible? So it is not possible, because between the two eigenspaces, those basis vectors, or basically any vectors chosen from each eigenspace, will be linearly independent with each other. So what does that mean? 4, 3, 4. We obtained 12 linearly independent vectors, right, from 10-dimensional space. So it is not possible at all, because we are considering 10-dimensional entire space, and so the maximum number of linearly independent vectors in total that we can have is maximum at most 10, right? So this 4, 3, 4 will not be possible. And so in that case, if we keep, still we do not prove it. I mean, it's not a rigorous proof, but if we keep the dimensionality of each eigenspace to be smaller than or equal to these numbers or algebraic multiplicities, and then at least when summing up their linearly independent vectors obtained from different eigenspaces, and their sum will be guaranteed to be less than or equal to the total dimension of 10, right? Any questions so far? 네. 네, 이게 그러니까 이 말이 그러니까 같은 아이겐밸류가 있다라고 생각. 문장이 약간 좀 이상한 것 같아요. 네. 하여튼 2차, 그러니까 두 개씩의 아이겐밸류 중근까지를 그냥 그 개수대로 중복된 거 개수대로 하나씩 다 카운트를 하면 하여튼 두 개씩의 아이겐밸류가 있는데 그 중에 이제 하나가 겹친다는 거죠. 네. 또 다른 질문 있어요? Right? So we will see when this kind of perspective is useful. Okay. Also related to this similarity transformation as well, right? And then let's move to the third chapter called diagonalization. It's closely related to similarity transformation that we studied. So this is similarity transformation, right? Okay, so so let's look at this example. We have 2x2 matrix, and then suppose we have P over here, which is an invertible matrix, and D is our diagonal matrix. And then we can verify that A is equal to PD and P inverse. So here A and D are similar, right? What's the meaning of it? They share exact same characteristic polynomial and thus exact same set of eigenvalues, including their multiplicities as well. So, yeah, this D. And D happen to be diagonal matrix. Okay? So D is diagonal matrix. But in the case of diagonal matrix, yeah, as I mentioned, we can easily find out its eigenvalues. What's the eigenvalues? 5 and 3, right? Again, in this case, yeah, if we applied maybe whatever formula to obtain the compute the determinant of this guy, and then its determinant will always be represented in this form, right? So this is already giving us this factorized form, and so diagonal matrix will just directly reveal the all the eigenvalues of that matrix, and this characteristic equation is the same as the characteristic equation of A, because yeah, as we proved in the previous chapter, the characteristic equation or polynomial between the similar matrix A and D will be exactly the same, right? So we can easily conclude that A has eigenvalue of 5 and 3, right? And then let's think of this situation. So if we can find some matrix P that is so over here, let's also think of this guy as D as this guy, right? And then if we can find such a P, then makes this similarity transformation output as diagonal matrix. In that case, it means we found the eigenvalues of A, right? So that's the reason why we want to transform the matrix A into diagonal matrix by using similarity transformation. Okay, similarity transformation will preserve the entire set of eigenvalues. Okay. Right. So this kind of thing by using the similarity transformation. See. Yeah, through this similarity transformation, we change the input matrix into diagonal matrix. That is called diagonalization. 이 대각화한다는 거죠. 어떤 멀쩡히 가만히 있는 행렬을 대각 행렬로 만들겠다는 뜻이고요. 그 대각 행렬을 만들 때 쓰는 이제 과정이 뭐냐? 그 similarity transformation 쓴다는 거죠. similarity transformation 써야만 eigenvalue들이 다 똑같이 유지가 되니까. But let's imagine the Gaussian elimination, and let's think of the reduced echelon form. And so reduced echelon form is actually the diagonal matrix. I mean, as long as we have the pivots in every columns, and then in the case of a square matrix, all the pivots will be aligned or placed along the diagonal, and the upper and the lower part will be all 0. So it is also another form of diagonal matrix that we can obtain through some transformation of input matrix A, right? And in this case, suppose this D is our diagonal matrix that we obtain as reduced echelon form, and then so like E1 and E2 and so on, right? So these are the elementary matrices that we apply in this particular order, and this matrix multiplication is all done on the left of the matrix A, right? So in this particular form, this is not a similarity transformation, of course, and right? So if we multiplied something over here, and then we have to multiply its inverse on the right. So that is called the similarity transformation, and only when applying the similarity transformation, the eigenvalues are kept the same, right? So here, the eigenvalue of an A and eigenvalue of D is completely different, right? Because our transformation that we apply is not a similarity transformation. It's not preserving eigenvalues. Okay? Okay, and then also it can be used conveniently to efficiently compute a squared and a to the power of 3 and so on. So in this case, suppose, so this kind of thing, I mean, this representation is called a diagonalization, and also we will see in the later slides. And if this representation and this representation is the same thing, right? We can move back and forth, so they are equivalent one, right? But this one is called a diagonalization. But in this case, okay, it can be viewed as some factorization of a given matrix into multiple matrices, right? So A is now represented as the product of several matrices, right? So it can be viewed as another form of matrix decomposition. So we studied about LU factorization and also QR decomposition or factorization, right? So both of them is representing the given input matrix A into the product of multiple matrices, and each matrix has its own requirement or conditions. In the case of QR decomposition, the first matrix should have also normal columns, and the matrix R should be upper triangular matrix. And in the case of an LU factorization, A is decomposed into the product of the two matrices L and U, and the L should be a lower triangular matrix, and the diagonal elements should be all ones, and the U should be upper triangular matrix, right? So each matrix factorization has its own requirement or condition. And also in this form of a factorization, what are the requirements? So P is invertible matrix, and that way we can define P inverse over there. And then also D is, the condition for D is that D is diagonal matrix, right? If we can find such a P and D, or invertible P and diagonal matrix D, and then if we can find this relationship or this equation, and then we represented matrix A into the product of several P matrices, and thus it is called some decomposition. Okay, but it is called eigen decomposition. And the reason why this one is related to eigenvalue and eigenvector, we will see the reason, or why it is connected to the eigenvalue and eigenvector. Okay, right. Then in the case of an A squared, if we use this eigen decomposition form, then we have P inverse and P, and so we actually don't need to compute this part because that is identity matrix, and so this guy, and this diagonal matrix squared, D squared, like 5, 3, and 5, 3, right? So in this case, it is simply 5 squared and 3 squared. And why is this so? So we have two columns, and then let's apply the column combination perspective. And so we have these two elements that is applied as a linear combination weight, and so it is column-wise scaling. Did I explain the row-wise and the column-wise scaling, right? When multiplying the diagonal matrix on the left, and it performs row-wise scaling, and applying or multiplying the diagonal matrix on the right, and then it performs the column scaling, right? So this column is scaled by 5, and this column is scaled by 3, which is the same value, right? And so we have this matrix as a result. And so okay, so we can utilize this product of multiple times of an A, and by using this eigen decomposition form, right? And also, yeah, in the case of this diagonalization, we still consider only the square matrix, but for some square matrix, we can find such a matrix P that makes this P inverse AP as diagonal matrix. But for some other matrix A, okay, which is a square matrix, there may not exist at all any such P that makes this matrix matrix A into diagonal matrix. So some square matrix is it is possible. I mean, for some matrix, it is possible to make to diagonalize the given matrix. For some matrix, it is not possible to diagonalize it. And so for those matrices that is possible for diagonalization, and then it is called diagonalizable. Okay, and it means if we can find at least one matrix P that makes like this guy into some diagonal matrix. So if there exists at least one such P, and then A is diagonalizable, for some matrix there exists no such P. Okay. And then when is the matrix diagonalizable, or when is the matrix not diagonalizable, which determines this diagonalizability. Okay, so yeah, suppose the matrix A is diagonalizable, and then we know this guy is D, right? And then let's just write it into this form. AP is equal to PD. Okay, and then we have maybe, let's consider 3 by 3 matrix, and suppose P is also 3 by 3 matrix, and then let's call each column of P as V1, V2, and V3. So it is AP. And in this case, what is the first column? I mean, how can we represent the first column? It is A times V1 and A times V2, A times V3. It is because those are working as a linear combination coefficient of these three columns provided in A, and that will form the first column of the resulting matrix, right? And for the second one, it is obtained by using this column as another set of linear combination coefficients, right? So we all quite familiar with that, right? Right. Then now let's consider this a PD, and P is this guy. So we have still V1, V2, V3, and then D is any diagonal matrix, right? And then let's represent or denote such a diagonal entry as lambda 1, lambda 2, lambda 3. So these are any arbitrary non-zero values placed along the diagonal, right? And then we know that it's performing the column scaling, right? And so lambda 1 times V1. So that is our first column of our matrix. And lambda 2, V2. Okay? So this is our second column, and the third column is lambda 3 and V3, right? Right, and then AP should be equal to PD, right? And so in this case, the first column should be the first column, right? The second, and so on, right? And so if we equate column-wise, given these two equal matrices, and then we obtain this guy. AV1 is equal to lambda 1 V1, and AV2 is equal to lambda 2 V2, and AV3 is equal to lambda 3 V3, right? Okay, so over here we suddenly obtained eigenvalue and eigenvector and their relationships, right? So finding such a vector v1 and lambda 1 satisfying this equation. So that was the definition of eigenvalue and vector pairs, right? And starting from completely different angle of this diagonalization, right? And then we changed it into this form, and then we obtained this equation. And what does that mean? What does it mean? The diagonal element of D, which are lambda 1, lambda 2, and lambda 3, are eigenvalues, right? And more importantly, and the additional kind of findings that we can obtain over here is the columns of P, okay? Columns of P should be eigenvectors associated with eigenvalues of lambda 1, lambda 2, and lambda 3, okay? So that is quite interesting kind of connections between this diagonalization and eigenvalue and eigenvector. Any questions so far? Okay, and then previously when imagining or when considering the diagonalization, we needed invariable P, right? So far, P should be invariable matrix, and we didn't know the actual requirement in terms of these P, but the only option or only possible way to form our P to make this diagonalization is that we have to form the columns of P as eigenvectors, and there is no other choice, right? So if we put some different column that is not eigenvector of matrix A, and then it means it will not be, it cannot be used for P to perform this diagonalization. Okay? So P, the columns of P should be composed of eigenvectors. And so here, so let's focus on this direction. So this direction is always true, but will it be true? For the other or reverse, the direction in a reverse order. So so in this case, let's just remove the last column of P, like this guy. Let's suppose P as being composed of just the two columns. Okay, in this case we will just remove it, and then let's consider D as just like this form. Okay, so in this case A is 3 by 3, right? So P is 3 by 2, right? And P is also 3 by 2, and D is only like 2 by 2. Okay, so still in this case this formula is true, but this equation is true, but will this be true as well? It will not be true. P is not even a square matrix, and we need invariable P, but here P is not even a square matrix. And also, suppose we understand each column of P each column of P is eigenvector, but let's fill out the columns of P as linearly dependent eigenvectors. So if we fill out the linearly dependent eigenvectors in the column of P, and then even if P is a square, P inverse will not exist, right? So in order to go back from the right equation to the left one, we need the assumption that P is invariable. And what does that mean? So in order to go back, or in order to obtain the left equation, we need n linearly independent eigenvectors. So that way we can form the square matrix of P that has a linearly independent columns, right? And so that's when the matrix A is diagonalizable. So in conclusion, when is the matrix diagonalizable? This is when the matrix A has n linearly independent eigenvectors. So in this case, A should have 3 linearly independent eigenvectors. Okay, so that's the condition for the diagonalization. I mean the diagonalizable. Right? And then let's think of this guy, geometric and the algebraic multiplicity. Okay, so in this case, yeah, we understand. We agree that geometric multiplicity is smaller than or equal to the algebraic multiplicity, whose total is 10, whose total sum is 10. But in this case, suppose the geometric multiplicity is strictly smaller than algebraic multiplicity. So the maximum value is 3, but geometric multiplicity is 2, and maybe it achieved maybe 2 over here, maybe 5. So this guy didn't achieve its upper bound, the maximum possible number of geometric multiplicity. So in that case, how many linearly independent eigenvectors can we obtain over here? We can only obtain in total 9 linearly independent eigenvectors. Does it make sense? So in that case, A is not diagonalizable. So from this perspective, geometric multiplicity should be exactly the same as its upper bound as algebraic multiplicity for all the eigenvalues. So this is the only case that makes the diagonalization possible. Okay, that's it for today. So we have a homework, right? So please prepare for it as early as possible. Okay, thanks.
마지막에 다이아고널빌리티 설명해 줄 때 잘 이해 못했어요.
다이아고널라이저블 한 게, 이게 여기서 지금 그러니까 사실 우리가 그러니까 이게 3x3 매트릭스면 지금 두 개 컬럼만 있어도 사실 AP, PD는 만족을 해요. 그러니까 뭐 이게 P가 그러니까 애초에 스퀘어 매트릭스가 아니어도 가능은 한 거죠. 근데 당연히 이쪽으로는 못 가요. 왜냐하면 인버스가 없으니까요. 그 다음엔 어떤 형태로든 스퀘어 매트릭스를 우리가 만들었다 치더라도 그게 다시 원래대로, 그러니까 이거로 가려면 그 스퀘어 매트릭스가 인버터블 해야 되는 거잖아요. 어떤 형태로 우리가 3x3이라는 매트릭스는 만들었다 쳐요. 아이겐 벡터들을 이렇게 잘
P요?
네, P를. 그러면 이 P가 지금 여기서는 인버터블 해야 되잖아요. 이 표현으로 가려면. 그러니까 P가 인버터블 해야 되는데 스퀘어 매트릭스로 그러니까 아이겐 벡터들을 쭉쭉쭉 나열을 해갖고 이제 어쨌건 n개, 그러니까 이 3차원이면 이제 3x3라는 그러니까 3개의 컬럼, 그러니까 3개의 아이겐 벡터들을 일단은 가지고 와서 쭉쭉쭉 나열을 하면 이제 3x3 매트릭스 만들었는데 좀 그게 이제 인버터블 하려면 그 아이겐 벡터 우리가 이렇게 쭉쭉 이렇게 컬럼으로 만든 3개의 아이겐 벡터들이 다 리니얼리 인디펜던트 해야 되는 거잖아요.
인버터블 하려면 그렇죠.
그러니까 결론적으로 다이아고널라이저블 하다는 건 뭐냐면 n개, 그러니까 이 매트릭스가 3x3이다 그러면 3개의 리니얼리 인디펜던트 아이겐 벡터가 있어야 된다는 뜻이고, 뭐 n/n이면 n개의 리니얼리 인디펜던트 아이겐 벡터가 있어야 된다는 뜻이에요. 이거 내가 굉장히 급하게 설명하긴 했지만 아까 이 지오메트리 멀티플리시티가 알지브레이크 멀티플리시티보다 항상 작거나 같다. 근데 알지브레이크 멀티플리시티의 합은 총 10이에요. 그죠? 그러면 여기서 10개의 리니얼 인디펜던트 아이겐 벡터를 우리가 얻어야 되는 상황이면 결국은 이 지오메트리 멀티플리시티는 이 알지브레이크 멀티플리시티보다 스트릭트리 작으면 이거는 그냥 꽝인 거예요. 이렇게 되면 될 수가 없고, 다 이 개수를 최대값인 이 알지브레이크 멀티플리시티와 똑같이 이제 나와줘야만 이게 얘네들의 합도 10개가 된다는 거죠. 즉 10개의 리니얼 인디펜던트한 아이겐 벡터를 얻을 수가 있다는 뜻이 되죠.
이게 아까 아이겐 스페이스의 디멘전이었죠.
네, 그걸 지오메트리 멀티플리시티라고 부르거든요. 근데 이게 뭐 왜 이거보다 작아야 되느냐, 이건 우리가 증명은 하진 않았어요, 사실. 네, 그렇긴 하지만 뭐 이거를 뭐 네, 그냥 증명이 없이 요거 하나만 우리가 인정을 한다고 치면 하여튼 요게 다 맥시멈을 다 이제 어치브를 해야 이게 가능해지는 거죠. 네. 네.
그 아이겐스페이스가
네.
다른 아이겐스페이스면은 다 그 거기서 나온 벡터들은 리니얼리 인디펜던트하다라고 했잖아요.
네.
그게 식으로는 이해가 되는데
네.
이게 그 도형적으로 그려보면은 만약에 3차원의
네.
평면인 아이겐스페이스가 두 개가 있다.
네.
그럼 두 개는 어쩔 수 없이 겹치게 되는 거지 않나요?
3차원에 이제 평면이 두 개가 있다.
네, 아이겐스페이스
그렇게 안 나온다는 거예요.
그렇게 안 나와요.
그렇게 한다는 건 뭐냐면 이게 첫 번째 아이겐 밸류에 대한 그 디멘전이 2고 쟤도 2라는 거잖아요.
아, 그럼 이게 넘어가 버려서.
네, 이게 엘지브레이크 멀티플리시티는 아마 2, 1이나 3차원이면 이렇게 나왔을 거니까 그거를 넘어서서 나올 수는 없다. 그리고 이게 뭔가 같으면 이게 어떤 컨트라딕션이 생기냐면 그 같은 벡터는 그러면 어쨌건 아이겐 스페이스에서 어떤 벡터를 잡든지 간에 A를 곱하면 이게 그 배수만큼 방향은 안 바뀌고 배수만큼 길이가 늘어나는 거잖아요. 그럼 그 벡터는 이제 아이겐 밸류가 만약에 1인데서 그러니까 뭐 3인데서 이렇게 나온 거다. 그러면 얘는 3배가 돼야 되는데 아이겐 밸류가 예를 들면 5인 얘에서도 또 이 벡터가 있다. 그럼 얘는 5배가 돼야 되는 거잖아요. A랑 곱했을 때. 그럼 이게 5배가 될지 3배가 될지 이거는 말이 안 되는 거잖아요. 그래서 컨트라딕션이 또 생기는 거죠. 네. 네.
이거 설명해 주실 때
네.
이거 뭐지?
네.
엘리멘터리 해가지고 이렇게
네.
만든 거는
네.
이거는 다이어고널이 아니라는 말이에요.
이 D는 다이아고널인데, 그러니까
네.
D를 우리가 RREF로 리듀스 스테이션 폼으로 만들면 다이아고널 매트릭스가 나올 수 있는데, 근데 이제 그러면 이제 이거의 아이겐 밸류는 D 자체에 대한 아이겐 밸류는 다이아고널 엘리먼트들이 아이겐 밸류가 되는 건 맞아요. 그렇지만 이제 A의 아이겐 밸류랑은 더 이상 D의 아이겐 밸류랑 전혀
다르다.
관련이 없다는 거죠.
그래서 요거랑 이거랑 다르다는 거죠.
그렇죠.
이렇게
네.
만드는
그러니까 이러한 그러니까 뭔가를 매트릭스를 왼쪽에 곱했으면 오른쪽에 그거 인버스를 곱해야만 이 나오는 매트릭스의 아이겐 밸류들이 오리지널 매트릭스 A랑 똑같은데 이건 왼쪽에서만 그냥 계속 주구장창 곱하는 것이기 때문에 이 나오는 매트릭스의 아이겐 밸류들은 오리지널 매트릭스 A의 아이겐 밸류랑 관련이 없다는 거죠. 네. 네.
헷갈려서
네.
말씀드렸죠.
네.
그 아까 말씀드렸죠. 저 알지브릭 멀티플리케이션과 지오메트릭 멀티플리케이션에
네.
그 지오메트릭 멀티플리케이션이
네.
이 어퍼 바운드보다 작으면
네.
그 다이어고널이 안 된다는 게 잘 이해가 안 돼서요.
네. 그러니까 이거의 합은 엘지브레이크 멀티플리시티의 합은 10개잖아요.
네네.
그러니까 우리는 하여튼 다이아고널라이제이션이 가능하려면 10개 리니얼 인디펜던트 아이겐 밸류를 얻어야 돼요.
네.
최대한 얻어야 되는 거예요. 10차원에서.
네.
근데 이제 이게 하나라도 작으면 그러니까 이거의 합은 10개죠.
네.
근데 이거보다 작거나 같은 게 지오메트릭 멀티플리시티이고 얘네들의 합이 결국은 우리가 얻을 수 있는 리니얼 인디펜던트 아이겐 벡터의 개수라는 거잖아요.
네.
얘네들끼리 리니얼 인디펜던트하고 이 개수가 이 하나 내에서의 리니얼
네.
인디펜던트한 베이시스 벡터의 개수니까요. 그러면 이제 이거의 합이 이 중에 하나라도 얘가 3이 2가 되고 얘가 2, 얘가 5면 그럼 뭐 9밖에 안 되잖아요.
네.
그러니까 이때는 이제 10개의 아이겐 벡터를 얻을 수가 없는 리니얼 인디펜던트 아이겐 벡터를 얻을 수가
얻을 수가 없어서 다이어고널하지 않다.
그렇죠. 네.
그러니까 무조건 그 아이건 벡터가 10개가 돼야 되는데
네.
그러면 이거의 합이 10개가 돼야 되는데 근데
그렇죠.
이 조건 중에서 널
네.
스페이스니까 이것보다 각각이 작아야 되니까 10개를 합을 10개를 만족시키려면
그렇죠.
각각이 이거랑
다
같아
똑같아야
될
되는
수밖에
거죠.
없는.
그러니까 이거 숫자보다 결국 작거나 같은 게 여기에 쓰여지는데 그거 합은 그러니까 10보다 작거나 같은 거죠, 당연히. 근데 그게 곧 10이 나와야 되는 거잖아요. 그러려면 이게 다 등호로 만족을 해야 된다.
어려운데.
네. 그러니까 한마디로 모든 디스팅트한 아이겐 밸류들에 대한 지오메트릭 멀티플리시티가 엘지브레이크 멀티플리시티랑 다 똑같아야 된다는 그 조건이 필요한 거죠. 네. 네.